All right. Well, welcome to lecture two for, oh man, it's supposed to be CS, whatever, CS 2810. So we previously learned all about vectors, right? Remember the notation of the size of the vector and what a vector looks like? Today, we're going to extend our knowledge to matrices. So, what is a matrix? Well, instead of just one column, a matrix is just bunch of columns enclosed by brackets. Just like vector, instead of one, we have multiple. Now, just like vector, they don't mean anything unless we attach meaning to it. Okay, so you can have vectors that look like this. You can have vectors that look a matrix that looks like this or these. And the way we can mathematically represent or tell people the size of the matrix is through this notation. Now remember, this tells you the dimension is 3, but now there are 2 dimensions. So x is 2 by 3. So it's 1, 2, there's 2 of them, and there's 3 columns, 1, 2, 3. So this is telling you the size of this matrix. Or y will be 3 by 2 because there are 3 rows and 2 columns. Okay? Now, matrix, they can take on any dimension, so any number here will work. Now, another thing you want to notice is that I made it very explicit that vectors are lowercase and most of the time cursive lowercase. Now, with matrix, we represent them slightly differently. We use the capital case. So this is how very often you can tell them apart. Now, we're going to go over some shapes. So a matrix that is wide is called a fat matrix. I didn't come up with a name. So that's if the width is greater than the height. So the width here is 3 and the height is 2, right? And therefore, this is called a fat matrix. So is this one. The width is 5 here and the height is 2. So basically anything where the width is greater than the height is in general called a fat matrix. Now we have the opposite, which is a tall matrix, where the width is less than the height. So for example, here's the width is 2 and the height is 3. So it's tall. Here's another one, and here's another one. Another matrix, if they're exactly the same, is called a square matrix. As you can see, is the size of a square, 2 by 2, 3 by 3. Okay? So we have matrix, just bunch of numbers, and enclosed in a bracket. Just like vectors, they don't really mean anything unless you attach meaning to it. Just like vectors, we can perform transpose. So how do you transpose an X? Well, the way you transpose a matrix is symbolically by adding a little t for transpose. So now you have a little t, and what you do is that you take the first row and turn it into a column. You take the second row, turn it into a column again. That's if you have a fat matrix. Okay, so you see, row turns into column. If you have a tall matrix, you can see it this way. A vertical turns into horizontal. Vertical turns into horizontal. That's it. So whereas vectors, you only go from vertical to horizontal for one single vector. You can imagine there are multiple vectors here, and you're going to do the transpose of this one and this one. So first becomes the first, second becomes the second. Okay? So you can imagine transpose of a transpose. So you take a transpose twice, you're just going to get the original matrix back. Okay, so now you want to take a second and see if you can find the transpose of each matrix. Okay, pause the video, give it a try. Okay, Now, let me move on. Remember that we previously learned how to multiply a vector by a constant. Here, we're going to multiply a matrix for a constant. So it's exactly the same as vector. If you multiply 2, what you're doing is multiply 2 by every single element here. As you can see, we're multiplying 2 to everything. That's it. Addition by a constant. Well, you just add everything here by a number. So notice I add a 2 to every single number here, and that's how I got the result. So multiplication by a constant, addition by a constant for matrix is really easy. We also remember the Hadamard product. The Hadamard product, we have exactly the same symbol for the matrix as well. When you're dealing with Hadamard product, you just take match up the element, the first top left with the first top left, and then you multiply them. And then you take the bottom one and then multiply them. And then you take the next one and then you multiply them. You can look through all these examples. They're all exactly the same idea. Like over here, we have 2 times A. So 2 is going to multiply by this. And then you're going to do the Hadamard product. So Hadamard product is very intuitive. What is actually more complicated is matrix dot product. Okay? The matrix dot product is written this way. So because matrix dot product is basically, I think, the most used operation, when you see two matrices next to each other, you can assume they're doing the dot product instead of the Hadamard product. If you have the Hadamard product, you need this symbol. But you don't need the dot here. You just put them next to each other and you know. The way we do matrix dot product is this way. You take this column and this row, and then you do dot product here. Just like the dot product we learned from the last class. After that, you take this and this. Now you do the dot product. And after that, you move on to here and here. Then you do the dot product. And lastly, you take the very last one, this and this, and you take the dot product again. So every one of these results in a number. So if you take the dot product here, that gives you a 1. You take a dot product here, that gives you a 4. Now dot product here, that gives you a 3. Dot product here, that gives you 9. So this is how matrix dot product work. Okay, so I said it here, matrix dot is the default. So the dot is actually not needed. Now, the key here is notice that Hadamard product, the dimension, the size of the two matrices has to be exactly the same. Exactly the same. But with dot product, because you're doing this and this, you need to make sure that the number of rows is the same as the number of columns here. So 2 and 2. Then you can perform dot product together. So in terms of size, this is what matters. And when you write them together like this, you will get the final result of the dot product. So take a second and make sure that this right here makes sense to you. Okay? The order of the matrix dot product cannot be flipped. We're often used to think that 5 times 2 is equal to 2 times 5. And therefore, you might think AB is equal to BA. And this is not true. They're not the same. if we have x and y here, for example, and let's multiply dot product together. Now remember, the dot product is here and here, right? That will give you this. And then here and here, that will give you this. The point is, if you were to multiply this out, you will get this. And if you multiply the opposite out, you will get this. And notice they're not the same. So since they're not the same, like this tells you, you cannot just flip them. This relationship does not hold. The diagonal of a matrix. So what's a matrix diagonal? Well, it's actually pretty intuitive. If you have a square matrix, that's a key. The diagonal of a matrix is a vector formed from the diagonal element of a matrix. So let's say you have a matrix, and then you want to find the diagonal of this matrix. What you do, you take the diagonal and make that into a vector. That is the diagonal. Notice I didn't pick this one. The diagonal is always this way. So this example here, the diagonal will be 4 and 1. See? So that's the diagonal of a matrix. Next, matrix trace. The trace of a matrix is the sum of all the elements in the diagonal. So basically, you look at that diagonal, and then you add them up. Like right here, you add them up. See? Over here is 4 and 1, right? You add them up. So the diagonal gives you the diagonal vector. The trace adds up the diagonal. Matrix inner product. Now, matrix inner product is very interesting because it's a combination of a whole bunch of things that we just learned. So it is defined, if it's symbolically written this way with 2 brackets, and it is defined as that you take the dot product of x and y, transpose. Okay? Remember what transpose was. And then you take the trace of it. Yes, I know. We just did the transpose, and then we just did the trace. So remember, the trace is the summation of the diagonal. So let's do a quick example. Let's say we have x and y here. X and y, and I'm gonna plug x here, right? And y here. So, and a little transpose. So first thing, if you remember how to do a transpose, we take the first row, turn it into a column, the second row, turn it into the second column. So there's no more t, we just used it up. Next, we're going to do a dot product here. Okay, to do a dot product, we have this times this, which is 1, and then this times this, which is 3. After that, we move on to this and this. And we're going to do the dot product here, which is 2. And lastly, this and this, which give us 4. So see how we go from here to here. And lastly, we do the trace. So the trace is the summation of the diagonal. 1 plus 4 is equal to 5. So if you know how to take the inner product, it's a way for you to essentially practice everything we just learned. Now, this function here is used quite a bit in machine learning and data science. So it's a way to measure the similarity between 2 matrices, and it's very useful. Okay. Now, you want to pause the video and see if you can find yx, basically the opposite. Okay. Take a second, pause the video. Okay. Now, okay. So if we do yx, then we just flip them. It's yx transpose. So we plug that in. Y goes here, and x goes here, plus the transpose. So first, we're going to do the transpose, this, and that becomes this right here. And then we're going to multiply them together, dot product them together. And you will see that the dot product is right here. So lastly, we take the trace. 1 plus 4 is 5. So they're actually the same value. Now, I don't know if I showed you previously transpose, when we talked about transpose, but I guess I did not. Okay, so there's an interesting property that I would like to show you. Is it this one? This one, yes. If you have x times y, and you want to take the transpose after you multiply them together, there's a very interesting property, which is this is equal to yx. So you flip them, right? Xy becomes yx. And then you put the transpose on both of them. So they're actually equivalent. That if you were to take the transpose after, it is equivalent to take the transpose first, then dot product them together. So if you had known this one, you could quickly see that this is what we need, and this is what we knew from the previous. We previously knew that when we multiply them together, it's 1, 2, 3, 4. Let me show you again. See, 1, 2, 3, 4. So if we take the transpose of 1, 2, 3, 4, we're going to flip them. So it's y transpose y, x transpose. Now we knew that transpose double cancels each other out, and then that equals yx. So this is how this is equal to this because of this property. And if we know that, then we know this is 1, 2, 3, 4, and we're going to plug it here. And all we have to do is take the transpose. Then we will get this matrix back. And notice when we take the transpose, we got 1, 3, 2, 4, which is exactly what we got here. Now, I am going through this fast on video on purpose because you could basically pause and go back and listen to it again. Okay, in class, we'll go over it a lot slower, but hopefully you are following along. If not, my video has infinite patience. You'll be happy to go back over and over again. Okay, now you want to pause the video and see if you can essentially solve these. Okay, pause the video. I'm going to move on. Okay, now let's, this page, it basically gives you the solution. So after you solved it, check them out, see if you can get them. Okay, we'll do a couple of them together. So over here, like problem 1, okay? So here we have y transpose times x right here, okay? So how do we do the transpose? Well, we flip them. So this becomes this. Now we just have to do a dot product. So this is a dot product. How do we do it? This one, give us the first number. And then you do this dot product, that gives us the second number. And then this gives us the third number. Okay? Now, this is a Hadamard product. It's very easy. You just take this and multiply by itself. 1, 0, 0, 0, 2, 1, 1, 1, 1. Okay, and then you can quickly see how we end up getting this. So this is a Hadamard product. And the third question here, we basically have 2z times y. So 2z, so capital Z. So 2z times y. Right here, 313. Plus 1, so plus 1. Okay. So how do we do that? Well, we can do them in any order. Like we can do them first or we can do them first. And it makes it a lot easier if you do them first because you make it a lot smaller. So I'm going to do that first. This times this is 3. And then this times this is 5. And then this times this is 7. Okay, so we basically combine this. So this is a vector multiplying by a matrix. Well, or you can see this as a one column matrix. Okay, now 2 times this is easy. Just 2 times every element. That's how we got this. And then we just add 1 to it. This is how we got the 7, 11, 15. Let's do a couple more. Let's see. I think these are too easy. All right. So these ones, go over them yourself. Like I've written down how to do them step by step. So I'm going to skip them here in the video. Okay, these ones are slightly harder. So they're symbolic representations. So instead of numbers, we have to do them symbolically. So V outer product. So this is actually just vector. So if you remember how we do this, we take this one multiplied by this. So x times x becomes x squared. X times y becomes xy. And you can see after that we take this and multiply by this. So that's how we got xy and y squared. Okay. Number 2, well, it's just a trace of this. Basically, you just add them up. Number 3, okay, so this is interesting. First, you can look at this and look at this and notice that they are the transpose. Actually, are they the transpose? Did I do something wrong? Oh, I did it wrong. Okay, let's do it together here. It's 1 0 0 0 2 1 1 1 1. And then alpha, beta, gamma. Now, if we multiply them together, it's alpha plus gamma. Oh, I guess. Yeah. Alpha plus gamma. And then it's 2. So you multiply this with this. It's 2 beta plus gamma. And then lastly is beta times gamma. So this is supposed to be a 0. So that was a mistake. But the actual final result is correct. Okay. Let's do another one. So Z, this time I think I copied it correctly. Yeah, I copied it correctly this time. Now, let's multiply them together. Let's take this and then do the dot product here, which is just alpha because everything else is 0. We'll do this again. So alpha is 0, but 2 beta plus gamma. So that's how we got 2 beta plus gamma. And the third one is just everything added together, alpha, beta, gamma. So anyways, you got the idea. We can basically represent all these equations with this like symbol, much more compact way of representing it. Okay, what I want you to notice from that exercise is that we can rewrite very large equations and compress them into the matrix format. Now, you can imagine when we do data science and machine learning, the number of data you have could be like millions, and like a million by million matrix, for example. That's really really large. But like, how do you represent that and manipulate them? Well, it's to do matrix, right? You want to write them like a matrix A could be 1 million by 1 million, 1 million by 1 million size. But you can very compactly represent that as just matrix A. So over here, what I'm saying in a very, very simple case is that, let's say we have this function, right? This is a function. Another way to write this function is we have 1, 3 times x1, x2. So that's one way to write it. Another way is this right here, because a dot product is equivalent to x1 times 1, x2 times 3. Oh, I made another mistake. This is supposed to be 2 here. Yeah, that's supposed to be 2. Anyways, you got the point that this and this are actually equivalent. And you can represent this horizontal vector by just calling it A. Or you can call it A transpose if you want to think of it as a vector. And X. So you have two ways of representing a function now. One way like this, which is the traditional that you see a lot. But of course, this gets very complicated if it's very, very large. And the second way is you can represent it like these. So an example of that is, imagine you have multiple variables, x1, x2, x3, all the way to x 1000, right? You don't want to write this because, well, it's just a pain. What you want to do is represent it with this vector times this vector. And now you can call this vector A or A transpose. Actually, A transpose would be more accurate, times X. So you can write this giant thing or you can write this tiny thing. So why is learning matrix and vectors useful? Well, once you learn how to manipulate matrix and vectors, it gives you a language to compactly represent very, very large number of numbers and variables, right? Right now, I just represent the entire 1000 variable with X, much easier, and 1000 numbers with A transpose, much easier. So from what we learned before, this is an example of a function defined such that you have 1000 input and one single output. Okay? And this logic actually applies. You can have a function for multiple input and multiple output, and it could also be compactly represented. Okay, so here's the example where the input is 2-dimension and output is 3-dimension. Okay, if we were to write out what we just learned, right here, we take this and we multiply this. And then we take this and we multiply this. So notice how that's how the first equation was formed. And now we got the second equation. And we do it again. That's how the third equation is formed. Okay? So now this is equivalently saying that you have input of x1, x2, and you have output of 3 possible dimensions. That's how we got like the input and output. Okay? Now, let's put a specific input, 1 and 0, right, into this function. What will happen? Well, if you put 1 and 0 here, that's going to be 1. You put 1 and 0 here, that's going to give you 0. And you put 1 and 0 here, that will give you 3. So you notice how we input 2-dimension, we got an output of 3-dimension. So why is why is like matrix, learning how to manipulate matrix useful? Well, it allows you to deal with enormous amount of uh, data variables as just a x. Notice this is a and this is x. So instead of writing this whole thing, it's just so much easier to write f of x is equal to ax. And then because you know how to manipulate matrices, you can do things such as ax plus bx plus cx, right? Right here. And then you haven't learned this yet, but you can essentially do a plus b plus c times x. It's not like it's not something out of your imagination, I assume. So, anyways, compressing large equations, all right, with multiple input and output can now be represented with matrix format. Like I just said, right here, you can represent that this way. Okay? So here are the commands for Python to represent matrices. The way you do it is you represent each row between brackets, another one, and another one. Okay? This right here is equivalent to a matrix. And right here, you already learned how to form a vector. Here we give you another example. And here is yet another example. So we have A, B, C, and B as a vector. And once you have them, right, you can do dot products. So A dot B, which is equivalent to doing this. And that it will just give you the result. You can calculate multiplication extremely fast using NumPy. So you don't have to do it by hand. Or A dot C, right, which is equivalent to multiplying two matrices together. Notice how the results are the same. So if you type this out, it would just calculate it for you. Now, this symbol, if you remember, is the Hadamard product. So the Hadamard product, A Hadamard D, and this will give you the right result. Notice they're the same again. Or A dot T, that's equivalent to transpose. Okay, so I transpose A, and then I dot D. So I transpose A and I dot D, and that will give me yet another one. Now, remember we had learned trace. So NP trace A, that's how you calculate the trace, the diagonal. So it's 1, 1, 2. That's how you got 4, because you do 1 plus 1 plus 2. Or you can simply get the diagonal vectors, right? Which is 1, 1, 2, 1, 1, 2, right here, this way. Okay, so for the last practice, I think this is it. You want to essentially look at practice converting these systems of equations into the matrix format. You want to know how to do this. This is a basic thing. And then you want to learn how to convert them back into a system of equations. And with Python, I would like you to essentially see if you can perform these operations. So make sure you know how to do this. Make sure you know how to do this. Make sure you know how to do this. So we learned matrix today, right? The idea of combining matrix and vectors is essentially allowing you to compress enormous amount of data into just a couple symbols. And then you can manipulate them through addition, subtraction, multiplication, whatever. Okay? So learn this well, and good luck.